In this program, we look at 3 buildings whose function is to harness the energy found in nature. We visit the giant solar furnace at Odelo in France and travel to De Norwig in Wales to see the mountainous hydroelectric pumped storage power scheme. But we start at one of the world's most successful wind farms.
Using the energy in the wind is nothing new, of course, and for centuries, small windmills like this have used the power of the wind to turn grinding stones or pump water for agricultural purposes. But modern societies consume enormous amounts of energy, and there are strong arguments for reducing our reliance on fossil fuels wherever possible.
Here in Sweden, on the island of Gotland in the Baltic Sea, energy is being extracted from the wind on a commercial scale.
This is Näsudden 2, the most successful wind turbine in the world, holding the record for the greatest amount of energy produced in 1 year, 7.7 gigawatt hours.
That's enough electricity to supply a community of around 1,500 homes with all the power they need. It's part of a large complex of turbines on Gotland, which are being used to develop even more efficient ways of generating power for the future. Wind turbines have to be in exposed positions, so they need to be simple to construct and maintain. They also need to be attractive so that they complement the natural landscape as far as possible. Näsudden 2's rotor blades are wider than the wingspan of a jumbo jet, and the concrete pylon is 77 meters high.
This gantry is used for inspecting the rotor blades, but it gives us a good chance to see the pylon. The pylon was built in 1982 for an earlier version of the wind turbine, a lower power model. It's built out of reinforced concrete, constructed by slip forming. That means the concrete was poured continuously while the shuttering was moved up, just like we are. The faint vertical marks you can see on the outside are left by the shuttering as the mould was pulled up the tower. Inside the wall, the concrete's heavily reinforced with steel bars that run up and down and all the way round, and that gives it the strength it needs to support the turbine on the top. The new turbine was installed in 1993. Like the old one, it was lifted up the pylon with its blades in position by winching it up these tracks here on the side. It weighed 200 tons and took 8 hours. They had to wait for perfect weather conditions to do it, which, as you can imagine in this part of the world, took some time. In fact, it was 3 weeks before there was a period with no wind, and they lifted it successfully to the top. They only just got there in time. After it was fixed down, the wind picked up just 1 hour later. We've locked the rotor so we can get out here and get a closer look at the huge 40-meter blades, one up above me and one down there below. They're made of a special lightweight carbon fiber composite inside a protective shell, so they have the strength and stiffness that they need. Even so, they still weigh 10 tons each, and when they're spinning, they're subjected to forces known as centripetal forces, trying to tear them off their mountings, up to 100 tons in each direction. So they're secured firmly to the rotor using this ring of bolts around the perimeter here. I'm in the machine house just behind the rotor. This is the gearbox here and the generator's just down below. It works just like the opposite of a giant electric motor. Instead of the motor driving the blades drive the motor, and that generates electricity. But the blades don't turn all the time. At low wind speeds, it isn't efficient to let them turn because all this equipment takes power to run it, 36 kilowatts in all. So when the wind is less than 5 meters a second, that's 18 kilometers an hour, the rotor's shut down.
The wind blowing on the rotor and the pylon creates a drag on the exposed structure, trying to blow it right over. Its weight is 1,500 tons, and the foundation weighs another 1,900 tons. All this weight helps to stop it toppling over in the wind. But the shape of the structure is also critical to the design.
The shape of the pylon helps it to resist the forces acting on it from its weight and from the wind. If it was a simple cylinder, like I've made from this road map, it would be easier for it to topple over or to slide at the base, what's called shearing. But its flared shape gives it several advantages. It's much stiffer in bending and more difficult to topple, but also because there's more area at the base, it's easier for it to resist that shear force. The pylon is cast directly onto the concrete foundation here, and it's this joint that's critical to the stability of the whole structure. Steel bars which are embedded in the foundation rise up the walls, and they overlap with the steel bars which run up the sides of the pylon. That's how the structure resists the shear force from the wind, trying to tear the pylon and the turbine away from the base down here. It's a great sight, even in the mist. Naisudon 2 only runs at 2 speeds, 14 and 21 revolutions per minute, which are the optimum for the generator. It's running at 14 RPM now, and it may look slow, but the speed at the tip of the blade is 211 kilometers per hour, and the acceleration is 8.5 gravities. That's nearly 5 times your scary fairground ride.
It's a fine balance between the cost of the whole structure and the amount of electricity that it will generate. The higher you are, the higher the wind speed and the more power you can harness. But the building cost increases very quickly. This is the optimum design for the most powerful wind turbine in the world.
Naisudon 2 is a prototype, pushing the limits of what's possible with wind power. We've seen that the wind turbine is a simple structure, easy to build and operate. While wind farms like this currently only produce a small proportion of the national need for energy, it's clear that in future they could make a much greater contribution.
Electricity is a modern convenience we all take for granted. Whenever we flick a switch, we never doubt that our needs will be met in an instant. The problem is that at certain times, like at the end of a TV program or during the adverts, millions of kettles and lights are switched on all at once. It's a daily problem that requires an instant response. The simplest solution is to harness another of nature's elements, the immediate power of falling water. The challenge would be to design a system that could work on an unprecedented scale. This is Dinorwig in Snowdonia, North Wales. Hidden under this mountain, below the level of this lake, is an instant response power station powerful enough to keep the whole of England and Wales from blackouts every day. Its construction required over 5 million tons of rock to be excavated and was the largest civil engineering contract in Britain's history, taking 6 years to build. It's the biggest hydroelectric pumped storage facility in Europe. Yet in spite of its size, it's so well hidden that visitors barely notice it at all. The locals call it Electric Mountain.
This is how it works. This is the mountain, and there's a reservoir at the top called Machlan Mawr. There's a tunnel that runs from the reservoir into the heart of the mountain and then down to the power station at the bottom, and another tunnel that runs out to this lake here. There's a gate at the top to control the flow and a surge tank to control the pressure. During the day, the water runs down the tunnel and falls down to the power station at the bottom, where it turns the turbines, and it's then expelled to the lake at the bottom. At night, when electricity is cheaper, the water is pumped back up through the tunnels and into the top reservoir, which is filled up again.
This overnight pumping is essential because the huge volume of water needed every day is too great to be replenished by rainfall or rivers.
This is the reservoir at the top, and it holds 7 million tons of water. That's 6 hours' supply.
The original lake up here was too small, so this dam was built to give the system greater capacity. Its elegant design blends smoothly into the landscape.
I'm deep inside the mountain, just below the reservoir at the top, and these two huge gates on either side mark the entrance to the tunnel, taking the water down the mountain to the power station. You can get an idea of the size of the tunnel from the size of the gates. They're absolutely enormous. This is the surge tank above the water intake tunnels. The reason for the surge tank is to absorb the water shock waves, a bit like the juddering in your pipes at home when you open or close a tap too quickly. It's a straight drop of 500 meters from there to the bottom. That's deeper than much of the North Sea.
As the water approaches the power station, the main tunnel splits into 6 smaller tunnels, each heading for its own turbine generator. The tunnels narrow to increase the speed of the water. There are more than 16 kilometers of these tunnels, all beautifully lined in concrete to allow the smooth transport of the water. This is essential, as any rough motion of such a large quantity of water could damage the tunnels. I'm now driving into the heart of Electric Mountain, down towards the station complex, where the falling water finally generates the electrical power. This access tunnel is about the same size as the main water tunnel.
Just imagine that running full of water at 18 kilometers an hour.
These are the 6 inlet valves connecting the 6 water tunnels to the 6 turbines. The instant these valves are opened, water rushes through, and in 10 seconds it's driving the turbines. It's like having 1,800 megawatts of power on tap.
That's the fastest response time of any power station anywhere in the world. This is the machine hall above the generators, and it's absolutely enormous. We're in a rock cavern, 2 million cubic meters in size. That's big enough to house St. Paul's Cathedral in London. The bare rock is reinforced with rock bolts, like this big one behind me, which are like nails drilled into the rock and then tightened up to hold it all firmly in place. The water finally comes out here in Llyn Peris, the reservoir at the bottom of the mountain. From here, tonight, it will be pumped back up through the turbines and the tunnels to the reservoir at the top. And tomorrow, it will all be back down here again, all 7 million tons of it.
To be able to generate enough power to run a city at a moment's notice every day is a daunting challenge. It was a bold decision to build a massive complex inside a mountain. But De Noorweg has proved an outstanding success, technically and environmentally. You'd hardly know it was there at all.
The instant power which De Norwig generates serves a nation, meeting a demand from millions for instant electricity. But the fundamental source of nature's power isn't wind or water, but the sun. What if we were able to tap the sun's radiation directly?
This is the huge solar furnace at Odélo in southwest France. Its purpose is not to generate electricity at all, but to trap sunlight and focus it onto a single spot, generating incredible heat over a very small area. It's the biggest solar furnace in the world.
The energy from the sun reaches the Earth here with a power of about 800 watts per square metre, say 8 light bulbs. Enough to burn you on the beach, but not enough for the scientists to work with. The challenge was to build a furnace that could focus over 1 megawatt of power onto a target little more than the size of a soup plate. Such a furnace would need to collect all the heat from the sun over a large area, over 2,000 square metres. That's 8 tennis courts.
By using an array of mirrors, this large area of sunlight can be concentrated onto a relatively tiny focal point.
The principle of the Odélo furnace is really very simple. This is the hillside. At the bottom of the hill is a huge parabolic reflector facing the hillside. It's 50 meters high. To channel the sun's rays, mirrors on the ground track the sun's movement across the sky and feed the rays into the parabola, which in turn reflects them to its focus, where the furnace is located. Each mirror is targeted at a different section of the parabola, but all the energy ends up at the furnace, like this, where the temperature can reach 3,800 degrees centigrade. That's enough to melt steel armor plating. This is Le Champ des Héliostats, the field of heliostats. A heliostat is a wall of mirrors which can be moved using motors to follow the sun, reflecting the sun's rays directly into the parabola. There are 63 heliostats on terraces up the hill, each one with 180 panes of glass. The glass on these mirrors is as flat as possible to reflect the sun's rays without distortion towards the parabola. Each heliostat is aimed at a different part of the parabola, and together they cover the whole surface. The area of all the heliostats is slightly greater than the area of the parabola to allow for some overlapping of the images.
Each one is controlled by a computer and can be aligned within seconds with the precision of 1/60th of a degree. That means that a sunbeam hits the same spot on the giant parabola with an accuracy up to 3 centimeters. The scale of the building can really be appreciated as you begin to climb the 9 floors behind the parabola. Even here, it's still 18 meters out to the focal point.
There are 9,000 individual mirrors on the parabolic wall. Each one is slightly curved to improve the concentration of energy at the solar furnace. The more perfect the parabola, the more focused and therefore the more intense will be the sun's rays at the target. Behind this facade, we can see how they're all mounted. Of course, the mirrors on this wall don't need to move, but they do need to be firmly secured against the wind and the elements, and that's what these grey mounts are for. The glass on these mirrors was specially heat treated so that it could be bent without snapping. This bolt in the middle pulls the mirror back so that it's curved. Each mirror was tuned by hand to its perfect position. It took nearly 3 years to complete. The mounts holding the individual panes are in turn supported by this steel space frame, which is fixed to the 9-story building behind. The building was constructed from reinforced concrete to minimize thermal contractions and expansions between winter and summer.
Such contractions could distort the shape of the parabola. We're 1,500 meters up in the mountains here, and seasonal changes are much more extreme than at sea level.
This is the sharp end of the laboratory, the furnace, where the sun's rays converge on this hole here. It's like being at the tip of a welding torch. Behind the hole, there's an experiment in this capsule waiting to be tested. It's a disc of new material, like this, which will be used in the heat shield of a space probe going to the sun in a few years' time. Conditions in this capsule are positively out of this world. They simulate the exotic environment close to the sun. Extreme temperatures, 2,500 degrees centigrade. I love research laboratories, it's great.
Odelo Solar Furnace is a world-class research laboratory where engineering and science come together in pursuit of new, high-performance materials. It's also an extraordinary structure, a building in which function entirely dictates form.
Harnessing nature's power on such a scale is one of the greatest challenges for an engineer. To capture the power of the wind in Sweden, the mighty force of water in Wales, or the heat of the sun here in France, required vision and ingenuity. In this extraordinary field of engineering, where special applications require special structures, we are only limited by our imagination.
In our next programme, we go underground on a journey beneath the seabed in Britain's deepest mine. Then we uncover an Olympic stadium hidden inside a Norwegian mountain, before returning to England to witness the final construction stages at London's latest and deepest underground railway station.